Hey guys, Stuart with Landon here. I'm going to go through a very simple kind of blockchain tutorial, I guess. There's definitely some mysterious aspects of the blockchain that I think a lot of people don't really get, but it's really pretty simple. So I'm just going to explain very simply proof of work. We're going to work our way up to exactly what it is in demonstration. So first thing we need to import is HashLib. So we have this library, and this has all sorts of fun stuff. So m equals HashLib. So what we can do is we can create a new hasher, we can call it, and we have all these different hash functions. So we have SHA-1, SHA-256, which Bitcoin's based off of. We have SHA-3, which is the newest algorithm, so much more secure there. Ethereum uses SHA-3. So we can create this, and basically what we can do is we can digest certain information. So the thing about hashing is that any amount of information can go in, and you're always going to get, in this case, in SHA-3, 256 bytes. If we want to use, as you can see, different algorithms, SHA-224, it's going to spit out 224 bytes. If we want to do SHA-512, it's going to shoot out 512 bytes. And so who cares, right? So the thing is that you can take any arbitrary size file. It can be hello world. Oops. Oh, that's right. There we go. And let's do this as the hex digest. It can be hello world. It can be, what we're going to do is we're going to make these instantiate each other, so we can just start fresh. So we have hello world, or we can have hello world, copy and paste this 7 times, right? Cool. What I'm going to do is I'm actually going to rename this to n so we can see these side by side. I'm going to print m, oopsies, hex digest, and then I'm going to do the same for n so you can see. Basically, now let's run through this. We're going to hash to spit out the hex digest for hello world. We're going to hash to spit out the hex digest for hello world 7 times, and then we're going to just print them. You can see they print out the same exact number, which is going to be 256 bytes, and that is a little bit different because a byte is not actually one character. It's a little bit different. So anyways, you get this spit out. So when you're taking a whole bunch of data and you're compressing it into the same amount of space, certain things are going to happen. Sometimes you might get 2 hashes. That generally does not happen. That's very, very, very problematic if it does. It's very unlikely that it would too. So if we instead say SHA-224, you can see it's a little bit shorter. This string's a little bit shorter than this. But I'm getting off topic. Whether you use SHA-224 or SHA-256, the odds of 2 pieces of data colliding or producing the same hash doesn't really matter, and you don't really know why that would matter yet. So why would that matter? So when you're taking a big piece of data, like a block describes a lot of different things. It describes a whole bunch of transactions, but you can also hash other certain things like a movie, right? Or some sort of book. Let's say we want to hash a book out, and we hash a book out in text, and we want to be able to quickly see if that book's in a library, right? So let's say we have this book, and it's going to be a byte string, some very, 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 very long book. It's going to be a very long book. Long book. Cool. So we have this very long book. What we can either do is say, if we're looking to search through a whole bunch of data, is we can say, hey, do you have this book? What are the contents? You can either use a title, but sometimes books have the same title. You could say author and title. Great, maybe you don't know. In a library, it's a little bit different because it's a library and you're using physical things. In a computer, you don't really say, I know the title of the book. Oh, do you know who the author is? Either yes or no. All right, you either have the information or you don't. A really good way to sum up a whole bunch of information is to hash it, and then you just have this little tag, and you know because the probabilities of two tags being identical is so unlikely, you can essentially compare very large pieces of data really quickly. So instead of looking through an entire book and saying, okay, is this data all exactly the same, and then we're comparing to a book that has this instead, these are going to basically compute two very, very, very different hashes, and then you just have to always consume, what is that, J? Then you only have to consume 256 bytes, right? And so if we have these, I'm going to do with the book here, and now it's one character off, right? We're going to use SHA-256 because we're keeping things standard. Dope. And then we're going to do the same thing, but with N, and book 2. Wildly different. You only really have to compare one character before you even understand these two different pieces of data. And again, when you're using the book analogy, it's very clear when you're looking at two different books whether they're the same or not. But at the same time, if you think about the Dewey Decimal System, you go and you try to find these things in Dewey Decimal System. I mean, you gotta go and you are several characters in and inside the row when you're actually looking and finding that book. Here it took one check and then we're done. So that's cool, right? What that has to do with a blockchain. So let's describe a block. A block is, in our case, it's going to be a dictionary, and we're going to have transactions. Now this transaction is going to be a list, and then each of these transactions, in itself is also going to be a dictionary, and we're going to have 3 of them. So basically, it's a payment from a party. We're just going to call this party A. To a party, which we're going to call B. And then an amount. So, amount. 10. 10 coins. 10 whatever, right? And we're just going to say it goes from A to B. And then we're just going to say B to C. We're just going to say C to D. Now this can also have arbitrary information, like sometimes when you push out a transaction, you have a message. Now this message could be, thanks for the help. I don't know. Pains. It's just a happy message. Okay. So you have this block. And now you want to be able, in a decentralized system, to agree upon this, that all these transactions happened really quickly. And these blocks, in terms of Bitcoin, would be like 1 megabyte, but in terms of Ethereum, could be a dynamic amount, a dynamic size, right? So it could be 1 megabyte, it could be 10, it could be 20, who knows, right? You want a way for all the nodes to agree, okay, yeah, did you get all these transactions? Because I did. And if there's any discrepancy that someone messed up somewhere or someone's trying to hack the system and attack it. And so what these systems use is basically a consensus protocol where they say, look, we can agree if the majority of people all are doing the same thing, it's legitimate. And that's when you hear about 51% attacks, because if 51% of the nodes are saying, I saw this information to happen, then you know, they basically have control and they can signal whatever they want and they can make whatever transactions happen because they're the ones who are producing the hashes. So when you're hashing things out, you're going to say, all right, sweet, we have this block. And this is not actually in byte form right now, so we can't actually hash it. So we're going to just import pickle. And if you don't know what pickle is, it just basically dumps things out into byte form, right? And now we can hash this. So we can say we're going to copy it, and we're going to hash it. And you can see, thanks for the help. All right. Cool. So just in the same way that we had the books very slightly variant, we can say, hey, I'm a nefarious person. I am B. I am party B. I'm going to take this and I'm going to change it to a lot of coins because I am evil and I want more money, right? And we're going to call this block 2. Now, in a system that's processing so many transactions all the time, you need a really quick way to say yes or no. Okay, is it true? Are these things the same? And that's where these hashes make sense, right? So n, block 2. So most of the nodes are going to say, this is the block I'm signaling, right? Because most of them are following the rules because it makes sense for everybody to basically abide by the rules. And it's very hard, being B, to say to 51%, make this transaction that benefits me. And they would say, why? I want a transaction that benefits me, not you. And you'd say, I got nothing. So basically B is going to signal out, and when the block gets filled and it's time to commit the block to the blockchain, you're going to say, all right, let's compare hashes. So you're going to have M as a hash digest. Oops. And then you're going to have N as a hash digest. And right off the bat, you're going to say, whoa, hold on. Something's funky, right? But if you have most of the people, because they are following the rules, this is what's going to happen. It's going to come in. You're going to say, okay, this is not a good transaction. I can tell without even knowing what's happening underneath it. I just know, right? And so this is the whole cryptography hashing aspect of the cryptocurrency. It's just using these cryptographic hashes. And because, if you remember, that it's so mathematically impossible to describe two pieces of information with the same hash, you can't actually describe a situation by which you profit that also is going to equal the hash of what is happening in real time and then be able to commit that to the blockchain. The sheer probability is just, it's ridiculous. Like, you can't do it, right? You might as well jump out of a spaceship into the atmosphere and try to land on a balance beam, right? It's the same, just there's no way it's happening whatsoever. And so what we can do then is, assuming this, is we can do some interesting stuff and we can create a really quick decentralized system because we can all agree really quickly on what these things are, and then we can commit it to the blockchain. Life's good for everybody. And so when somebody comes back and looks at all these blocks, what they basically see is the top block. So we're going to write a top block where something like this happens, but there's more information in it. Basically, we have to know what the last block was, and because we know that these blocks are being produced in a way that's benevolent, we know that the last block was also legitimate, right? If the last block's legitimate, cool, then we go and we check out that block, and that block is going to essentially say the same information. These are the transactions that occurred. This is the hash of the last block. You can go to the last block and then you can hash it. You're going to get the same exact hash. That's how you prove that these things happened. So last block is just going to be some sort of hash, right? And that would be some sort of digest. And we could say, you know, this is the last block. That's actually not what it's going to be. It's going to be m.digest, right, in this world. And then there's something called nonce. We're going to set this as 0. So we've got this block, top block. There you go. You can see it's a gobbledygook. But for the sake of legibility, let's do this. So now you're probably thinking, cool, but Bitcoin's all about mining, and all I hear about is mining, people making money from mining. So you are talking about mining, and I thought that was where the hashes come in, and that's true to a degree, but it's true for both, right? You do hash when you're mining, but it's not for the same reason that you're hashing for just basic cryptocurrency. So the basic cryptocurrency, it's to quickly confirm with every other node in the system that this block contains this information without going through every single transaction and looking at every single one. That's way too slow, right? Ironically, because blockchains are slow, which I'll get to. But then that allows us to then say, okay, this is what the hash is, and put in the hash of the last block in, and you basically chain them together all the way down to the Genesis block, a blockchain. All right, cool. So when we're talking about mining, though, it's an arbitrary system, and the only reason why we do this is because it seems like it works to essentially reward people and to make sure that the consistent amount of transactions is happening in a block. And so what you introduce is this thing called difficulty, right? And let's hash some sort of block, right? We have this nonce, which is just this little tag. We're going to basically do the same thing. It's going to print out a different string than what was the last block, and that's great because you're starting to understand why these things happen and how they do happen, right? And so the block before was this, and now we included it in this, and now this is the hash, right? Cool. Proof of work is a way to essentially randomly distribute some sort of currency in a blockchain system. So even though you can have a blockchain with whatever you want, it could be recipes, pizza toppings, it could be your favorite place to go travel, all right? It doesn't matter because you're just hashing it, and if everybody can agree upon what the hashed information is, then it's fine. But because we're working with an economic system, right, there needs to be an introduction of the currency into the system. And so that's where proof of work comes in. Now, proof of work basically says, here's a challenge, and the answer to the challenge is unknown. Nobody knows what it is, but there's a parameter by which it's really easy to check if you got the answer, and then if you get the answer, you win the blocks, and you can't predict what it is beforehand. And you're like, this is odd. But if you also think, okay, well, you can't predict hashes ever, right? And so what I had said before is that it's impossible for you to essentially inject information into a block and know what that hash is going to be in the way that you're going to game it before it starts getting hashed, right? That's what a nonce is. So basically, you have some sort of difficulty. You're going to set the difficulty. Actually, I already did this, so I'm going to copy and paste it from here. And where are you, difficulty? We have a difficulty of 1, which is arbitrary, and then we have a difficulty string, and this is basically the challenge, right? The system's difficult and only accepts the correct answer if the hash is led with difficulty string. And so it's led with a 0. And you can see we hashed this block. It is not 0 though. So if you're going to say, I'm not going to commit anything unless the hash begins with 0, you need to modify this data somehow. Because if you notice, top block, okay, everything's there. We need to inject some information to essentially make it spit out, you know, a hash that starts with 0 somehow, right? Without modification, it's this. So what we can modify is this nonce variable. This is just basically a little indicator, piece of data that completes the puzzle, which is like, make me a hash that starts with 0, right? So what we're going to do to demonstrate is I wrote this little piece of code. Basically, it sets the nonce to 1, and then we're going to, this is the top block. So the top block has a piece of data in it called a nonce. We're going to set that to 1, and while the digest of this, we're going to change it to like, oh, it's actually in there. We're going to change it to P. While the digest, which is a string, the beginning of difficulty, up to the beginning of difficulty, does not equal the difficulty string, right? So what we're basically describing is, while whenever you get out the hash of the block and the up to the beginning of the difficulty, which is 1 in this case, it's not equal to the difficulty string, which is 0. And this basically is saying up into the first character. And so we chop this all down, and we basically get this. Well, this is not true. Add 1 to the nonce, modify it into the block, create some new hashing object, hash it, print it out, and then we're going to do the check again, right? So what you're going to see is essentially what we're spitting out is the nonce, right? And now it tried it with 2, didn't work. Tried it with 3, didn't work. 4, 5, 6, 7, 8. What it's going to be, actually, what we should do is spit out the block as well. Or let's spit out the digest of the block. So it goes through and it hashes. Okay, where does it start with 0? Boom, starts with 0. Awesome. So it took 26 hashes. So what if we modify the difficulty to 2? Now we have two zeros. It's going to take longer, right? So let's do it again. Okay, that took 145 milliseconds. Or hash. There's the 0 there, but we're looking for 2 zeros, right? I wonder if we can, we probably are going to, yeah, hit another 0 before that, but we're not interested in that. So we're going to hash this 500 times. There we go. Boom. There's the hash. And if you look at the top block now, there's the nonce. So that's what completes the block, right? And now it's going to get exponentially more difficult to find this, and you're going to have to work harder to complete that. But once you have this little tag, this little nonce, this number, that completes the block, and that's when this all gets committed to the blockchain. So one more, and you can see that took a lot longer, right? A lot longer. And oops, there you go. Pretty cool, right? And 4, I forget how long 4 takes. Might take like 30 seconds. There you go, 11 seconds of power. Boom, there you go. Cool stuff, right? And so the difficulty in these systems gets dynamically adjusted. So when you say there's a block time of like 20 seconds or 10 minutes, what that's saying is that the average solution to the problem should be around that block time. So sometimes it happens before, sometimes it happens after. But the difficulty is dynamically updated to fit within that realm. And so if we had two hashers on this network basically coming at it from different angles, it would get done take half as much time, right? And so then we'd have to make the difficulty twice as hard. And that would dynamically increase. So you basically keep the amount of blocks that are getting committed static over time. And this is just the way that you can introduce this cryptocurrency into the ecosystem without knowing beforehand. And thus it's fair. However, it also caps the amount of transactions a second, because while you're hashing, you can't add more information to it. Otherwise, it completely changes the data and you get completely different hashes. So you have to sit on the information. All right, we're working on this block. Only so much can go in. It's full. The block is full. Start hashing it. And then only once we have the solution, it goes onto the blockchain. And then you take the transactions that are pending, boom, put on the block, keep on doing the same thing. So this is why transactions aren't instant on the blockchain, because this hashing is going on to find the solution. Now, that's probably not the best way to do this. And because one, it's super energy just sucking. You know, if you run this script in your computer, and I've done it for like 5, it doesn't, I've been letting this thing run for like 4 or 5 minutes, and it's just, you know, the heat vents are going crazy. All that wasted energy is just, what is it doing? Nothing. It's just going through every single one of these and finding what's up, where's the nonce. And also it limits the capacity of the network because it's capped. And so if you've heard of what's basically like the mempool or transaction memory pool, is where you submit blockchain transaction, Bitcoin, right? And it takes so long because it gets put onto a stack, a whole bunch of different transactions, and you know, you're last in line, you're going to get served last. So once the block, the current block is committed, new block comes in, pumps a whole bunch of transactions, fills up the block like a bucket, starts hashing, and you gotta wait until, you know, the transactions are up until you get committed to that blockchain. And that's just how it works. And so the throughput of these systems is very slow. But so it's a conundrum. No one has really been able to come up with a better system yet. Or a better system that's provably as fair or as battle tested as this. And so it'll be interesting to see. But I hope that gives you a basic idea of what is happening in a blockchain, and I'll probably add more of these little snips in for you later. So, all right, thanks guys.